Hey everybody, Mr. Woz here, and welcome to another episode of Wozley Science. This is the second part of our natural resources unit. In this one, we're going to be focusing on energies and mining. So, let's get started. Okay, so we got three topics in this video. We're going to get into types of land, and then we're going to get into non-renewable and renewable energies, and then last, we're going to cover mineral extraction. The NGSS DCIs that I'm covering in this video are all the Earth and Human Activity ones for high school level. Alright, so we're going to get into how the different surfaces of our land have different sorts of things going on and how humans have affected them. So the first thing I wanted to get into was the polar regions, the Arctic in the north and the Antarctic in the south. So only 10% of the world is covered by this ice. As we know from previous units, it has a high albedo effect that is able to reflect incoming solar radiation. But due to climate change, these areas are melting. If we take a look at the United States, let's focus on that first. The first type of land I want to focus on is this dark green area called the evergreen needle-leaf forest. These are the tall trees that you see in Star Wars, in the Endor moon with the Ewoks, these tall redwood forests. These guys soak up so much carbon dioxide from the atmosphere, and they are endangered in the Southwest. What's happening is a lot of them are being cut down. If we focus on another type of forest, these forests on our side of the United States are more seasonal. Their leaves fall in the fall and then they regrow in the spring. They are facing increased precipitation and dramatic temperature fluctuations. Then you have the open suburb lands in the desert. These areas are facing hotter and drier climates, and increased water demand in these areas is also a big problem. And then we have the grasslands in the Great Plains. They are very important for recycling nitrogen and carbon. Grass grows fast, unlike trees, and they are most likely the area to be turned into cropland, but that's declining very fast. So then we have the croplands. Now, yes, we focused on agriculture in the previous video, but I wanted to give you a visual of how much of the US is covered by specific crop land. This is where the farming occurs, and this area is vital for growing our food. It's commercially grown in the Midwest and in California, and this land is 60% or more that is solely farms. Now, if we look at other places like India and China and Europe, just look at how much is dedicated to cropland. It's pretty crazy. This is the necessity for feeding some of the most populated areas of the world. But what I ask of you is it sustainable? Now let's go back to the US. This land is also used for farming. We can see some areas in Florida and some more areas of the Midwest that are closer to the East Coast. And these areas are for farming, but less than 60% of the land is solely dedicated to crops. Now, what I wanted to show you here is that these red spots represent urban areas. And yes, they look really small, but what they're showing is that 60% or more is specifically like pavement and buildings. These areas can be very prone to flooding because pavement, as we learned previously in the year, is impermeable, which means that water can't get through it. They have to have a very strong sewer system to combat this. New York City is very susceptible to flooding due to this. And then on the other side of it, it also has sea level rise going on. And if we look at this last type of land, we have the barren or sparsely vegetated areas. And you can see much of the pretty much the entire northern part of the African continent is this way. These areas barely have any vegetation. They're difficult to live in. They're difficult to grow food. You need lots of water in deep wells. They're required in order to grow any sort of food. And in some areas, like Saudi Arabia, have to use distillation for water access. What does this all mean? This means that these different types of land yield different resources that we as humans are very interested in having. If we look here, this little black trapezoid, those represent mineral deposits, and you can kind of see that they're all around despite whatever type of land that you see. But what ends up happening as a result is there's different types of minerals in these areas. We also have a lot of fossil fuel reserves. A lot of those fossil fuel reserves are actually happening in areas that we just saw previously is sparsely vegetated land. So that's pretty interesting. And what's happening that we can see on this, and we talked about soil in the previous video, but the soil quality around many areas of the world right now is not great, in not great shape. And so the different plants, temperature, and the moisture will create that different soil quality, but it's up to us to sort of keep that soil alive. Okay, we are ready for non-renewable resources. These are known as the fossil fuels. There is coal, petroleum oil, and natural gas. They are the non-renewable resources that we have a limited amount. We are using them faster than what the earth can create more of. 80% of the whole world's energy comes from fossil fuels. Only 20% of the world's energy is either nuclear power or all the other renewable energies that we're going to be talking about in a little bit. They are overall, the fossil fuels meaning, relatively cheap, they're efficient to get, but what I ask of you is at what cost? Once these fossil fuels are extracted from the earth, we are then able to burn them in power plants. They give off huge amounts of heat when they get burned, and right above this area where they get burned spins these turbines and connects to our electric grid. There's a really cool video right here that I will post as a link to this video so that you guys can check it out and see how like electricity is produced. Coal and natural gas are the two that are mainly used for electricity. Unlike natural gas and coal, oil is really a jack of all trade, master of none, because it has many purposes. 2/3 of it goes into transportation, but you can break down that into a bunch of things. Cars, the motor gasoline is a chunk of it, but there's also diesel fuel and jet fuel. And then you can take the hydrocarbons and turn into gas liquids and use it for things like propane. And then besides that, it's used in an industrial amount for heating and plastics and pavement for our roads, cosmetics, like it's what lipstick is made of. It's used for so many different things. So just to give you a brief overview where fossil fuels come from, they are concentrated hydrocarbons left behind from the ancient swamps and phytoplankton that fell to the bottom of the ocean tens of thousands of years ago. And they take tens of thousands of years to make. And what is happening is that we are using it much faster than it can even form. We can see that when we talk about the EROEI, which is the energy invested to produce a barrel of oil compared to the energy that you get. If we look to the right over here, we can see that right now we are the second largest consumer of fossil fuel on Earth. China is number one. They're dominantly using coal right now, where we are using an even amount of natural gas and oil pretty much. And so you can see just how much oil we consume in America compared to the rest of the world. In 1950, pretty much all the oil that you got out of the ground, you then got to use, because it barely took any energy to even get the oil in the first place, because the oil available was very shallow. You didn't need a whole lot of pipes like you do today. So now today what's happening is you really only get about 10% of the oil that you dug out of the ground. 90% of it gets lost through the getting the energy itself or transporting it. And so at this point, using fossil fuels is just incredibly inefficient. Renewable energy only accounts for 12% of our energy consumption. It's important to note that this is electricity, but also transportation.
And so what you can see here on the pie chart, of that little green slice, you can then break down the kinds of renewable energies that we are currently using. You can see most of the world is using biomass, and followed by that is wind, hydroelectric, solar, and last geothermal. Energies that do not release CO2 and do not require us to dig it up or drill or extract are vital to our future. There is no one size fits all though, and the solution depends on climate, topography, and population. We must raise this 12% higher to a higher number every year. So how are we going to do it? Well, we're going to bring out the best.
Okay, so I just got a new mic, so if it sounds a little different, I apologize. My old mic was about 14 years old, so hopefully this is an upgrade for this video. I'm now going to be talking about renewable resources because this is the pathway to getting away from the fossil fuels and using energies that are much more sustainable. So my goal is to give you that overview of each of the renewable energies and then show you where in the US they have the greatest potential. First off, let's talk about solar energy. These come from photovoltaic cells. What's happening is the photons, which is energy from the sun, becomes exposed to the metal of the panels, which makes electrons then become released. The electrons then travel through DC current on wires and then eventually can travel to an AC adapter, which converts the electricity from DC to AC, and then you could run the energy that's happening off your rooftop into your house. Most of the time though, what's happening is the electricity is going into the power grid. It's being then collected by your power company, which in our case in Connecticut is Eversource, and then they just essentially sell you energy back, and that's how it works. Now you can also have solar farms, which are large areas of panels which might be owned by a company or leased from like a farm or something like that. You can also have solar water, which uses the solar panels to then heat water to heat homes. This actually is a really efficient thing that we don't see enough of in New England. You can also have batteries in your home that can allow you to charge up the batteries during the day and then use the energy at night. So if we look at the US, it is quite clear that the Southwest is the best place to have solar energy. You're going to get the most bang for your buck there. You can see that other places around work out really well too, but not a whole lot in Connecticut, but yet you still see lots of houses with solar panels on them. The next energy I want to talk about is wind energy, and this involves wind spinning a turbine, and then there's resistance on those blades that then can make electricity. It's a very, very simple energy transformation. You can have onshore wind, which involves turbines on land. They're closer to people, but they can be more efficient, meaning that the electricity from the turbine itself has less distance to travel. Offshore wind will get more wind, but then the electricity itself needs to travel a longer distance, so you lose energy along the way. There is now more micro wind turbines, which would be like your own little wind turbine on your house. Now, if we look where in the US has the most wind energy, we can see that obviously the shore is where you would get the most, but in the Great Plains is where you see the most potential wind energy. Kansas, Texas, Oklahoma, those areas there have the highest wind potential. Now I'm going to talk about hydropower, which is getting energy from flowing water in rivers. Essentially what's happening here is you set up a reservoir on one side of the dam that then fills water at a higher level than the other side, and the only way for the water to go through is to travel like down, almost like a waterfall, and then it will hit turbines, which will then spin a motor that are then hooked up to generators, and then those generators are hooked up to our electric grid. So unlike solar and wind, it works around the clock. Unless the river, dries up, of course, which that's happening actually in the Hoover Dam. it can give communities control of their water for irrigation and conservation, and actually create the reservoir can become like a park, meaning like a place for like people to go fishing or boat recreation, things like that. One challenge that hydropower has is anadromous fish such as salmon that are born in freshwater then need to go to the salt water, the ocean, to live, is they have to go up the river, and if there's a dam there, they get stuck. They can't get past that point. And this has created a lot of problems in Washington and Oregon and Alaska. If we look at where there is the best potential for hydropower, it's actually Washington, Oregon. Alaska's not on this, but Alaska is great as well, and California. On the East Coast, you can actually see it's North and South Carolina and Georgia and New York. So New York actually has a lot of hydropower dams already. Other places in the US are not so great. All right, biomass, which is currently the most used renewable energy. So what is biomass? It's essentially burning leftover agriculture, forest, and urban waste to get energy. Carbon dioxide does get released from this, from the power plant itself. So that is something important to note. Now, why is burning trees considered renewable? Well, trees take a lot shorter amount of time to grow than coal, oil, and natural gas. So that's why it's considered renewable. But people debate this. What is used to burn was going to release the CO2 anyway through decomposition. So that's one argument that gets made. You can have what are called methane digesters, which we actually talked about in the part 1 video to this, which is using livestock waste for energy. And then biofuels becoming more and more popular with trucks for transportation, which is using crops such as corn to then turn into ethanol gasoline or biodiesel that the vehicles like trucks can run off of. So let's look where biomass can be produced the most, and the winner of this one is truly the Great Plains, but also the Midwest. We can see a huge potential for biomass because they already have so many crops, and the fields, the grasslands can grow trees that can then be chopped down pretty quickly and then utilized. Geothermal is the least used renewable energy in the US currently, because it takes heat from the earth to then get steam to spin turbines. It's very reliable and it's very consistent. Iceland is the most used area of geothermal energy, but that's because Iceland is a volcano. It's a giant volcano. It's only working well in areas that have serious volcanic activity. If we look at the potential, we can see essentially Yellowstone Park and things around it are the best place in the US where you can have geothermal energy. Most of the West Coast has a potential for this, but the East Coast does not.
The last energy I'm going to talk to you about is nuclear power. So nuclear isn't necessarily a renewable resource. It's more of an alternative energy because it does require uranium to be mined and then enriched. And on top of that, the uranium gets turned into fuel cells that then go into the nuclear power plant for an atom to be split and then cause a process called fusion. You're left with fuel rods that are spent, and so those have to get buried somewhere for tens of thousands of years because they have radiation, and you don't want to be anywhere near that. So the heat drives a steam turbine that then gets used for energy. What's really cool about nuclear power is you can get such an enormous amount of energy from only a little bit, and also it doesn't release any CO2, unlike biomass. It can produce more energy than any of the other power plants of ways that we get electricity from. It's a really good choice for places that are heavily populated that don't have a lot of availability in things like wind or sunlight. So now we're going to get into our last piece of this video, which is about mineral extraction. So the first thing I'm going to do is talk about the 5 types of minerals that get mined out of the earth for use. They all have different purposes, they all have different value and different formation processes and in locations around the earth. You don't need to write all of this down. I think just jotting down a couple of these minerals and the types that they are is really helpful in terms of just getting a little name recognition, but you don't need to know all the purposes. I think it's just helpful for the exposure component. So the first type of mineral is the metallic minerals. So you got iron, copper, aluminum, gold, silver, lead, zinc. These are all things that are used like buildings, electrical wire, construction, but also then some jewelry is part of all of this. So then we have the non-metallic minerals. So limestone, gypsum, salt, graphite, quartz. You got things like cement, fertilizer, even food seasoning with the salt. Batteries, again, are a big component. We saw batteries on the last one with lead. So then you got the gemstones, right? Diamonds, rubies, sapphire, emerald, amethyst, topaz, opal. So these are all used for jewelry mainly, not much other things. Diamonds used as cutting tools for cutting things like tile. For energy resources, these are also mined. You should be familiar with these. You got coal, oil, natural gas, and uranium. And then for our rare earth metals, these are getting more and more popular right now as we are trying to have more things that are battery powered. Lithium, cobalt, nickel, neodymium, that's a very powerful magnet. These are all the different things that we dig into the ground to mine for. Let's now talk about the types of ways that we mine. So the first one, there's going to be 4 of them. I think all you need to write down is the name in the process and then maybe like one other thing here, because this is a lot of information, but I just think it's the exposure piece that matters. So the first type is surface mining. This is the most common one. It involves extracting minerals from the Earth's surface by literally removing the ground that's in their way from the mineral. Lots of rock and soil gets moved, all the vegetation gets removed. We do this for coal, copper, iron, gold, phosphate, diamonds, and a lot more too. It has benefits because you get everything that's in there. It's safer for the workers. They don't need to go underground and then get exposed to black lung, or they don't get crushed if the mine collapses. There's a lower extraction cost per ton, which means they can get more money out of it, and it has a high mineral recovery rate. It has a huge environmental impact though. It causes deforestation, habitat destruction. The land is like completely gone, and it can have a high operational cost. A lot of machines are needed, a lot of labor is needed, and most importantly, it could cause some serious water pollution because all this stuff from the mine can mix with the local river or stream, and that could lead to a lot of big problems. The next one is underground mining. So this is where instead of removing the entire ground above, you go into the ground with these huge drilling machines. So you could be mining deep below the surface using tunnels, shafts, chambers, things like that. We use this with a lot of similar minerals that you saw previously. It allows extraction for deep-seated minerals. There's less surface disturbance. It can extend the mine life beyond just surface mining. Now, here's the problem. There's a very high infrastructure cost for doing it this way. You need ventilation, and you've got to check your safety. It can have problems with the miners themselves. It takes a long time for this operation to work, and you can also have groundwater contamination. So the third one is placer mining. So this is when you get the minerals from riverbeds or beaches by simply running it through like a sifter almost. It has a low startup cost. It's very simple to do, have minimal infrastructure required, and it works well with valuable minerals like gold. This was happening a lot on the West Coast back in the day, the whole gold rush. Now, the cost could be the sediment can get disrupted. It can affect aquatic ecosystems. It can be labor intensive, and you could eventually start having erosion and pollution issues if you're doing this at a large magnitude. And the last one is in situ mining. This is when you extract minerals by injecting chemicals and water into the ground to dissolve the minerals around it and make the mineral that you're trying to get to almost pop up or just be completely exposed so then you can grab it. We do this with uranium and copper, but also natural gas. That's called fracking. It has lower labor and equipment costs. It can be much safer for the people than being underground. and it's pretty energy efficient for certain mineral types. It has huge costs. It is a risk to groundwater contamination. This is what's happening right now with fracking. It requires careful environmental monitoring because of this, and once the chemicals are in your drinking water, like, you can't get them out. We're going to finish this video with the best thing, math. So what I'm going to do right now is break down how you can calculate the profit from a mine. Here's what we look at when we are doing these types of calculations, and we are going to be doing this in class. Will it yield a profit to the company? Will this damage the environment too much? Is there a need for this mineral? What's the best type of mining to do with this area? And what is on the land? Is it protected? Is it near a community? These are all things that get considered when we decide to build a mine. So how does the math work? Well, we first start by looking at what the mineral is and like how much is it worth. We then look at how many grams of this mineral is averaged to be in the volume that you want to dig up. You then have to take the actual volume of the potential mine, and it just becomes a amount made sort of situation with how much will it cost for the mine for every volume. When you take that and then you take the volume of the potential mine, literally length times width times height, and then you say, are there additional costs? And so those are all the components that we do to figure out how much this mine is going to cost. And so then it just simply becomes amount made minus cost will equal profit. So now let's look at an example. So in this situation, a company has discovered a deposit of copper ore beneath a rectangular area of land measuring 1.5 kilometers by 0.8 kilometers. They want to go 30 meters deep. The average concentration of the ore is 1.2%. So within this whole volume, 1.2% of it copper ore, whereas 98.8% of it is just stuff you gotta move aside. The density of the ore is 2.7 grams. So we got to figure out how much money they can make off this. So the mine and processing will cost us $60 per metric ton of ore. The selling price of this pure copper is $9,000 per metric ton. And the environmental remediation and the land restoration is going to cost us a one-time deal of $2 million. So there are 7 steps here that we have to take. Let's get started with it. Step 1, we calculate the total volume of the ore. So we're going to change the kilometers into meters. So 30 meters times 800 meters times 1500 meters will get us 36 million meters cubed. All right, so we got our volume down. Now it's time to figure out how much copper ore there actually is. So we got to convert this volume into mass. So we do that by multiplying its density times the volume. So when we take the density and change it from 2.7 grams per centimeters cubed, it becomes 2,700 kilometers per meters cubed. You times that by the volume, you get 97,200,000,000 kilograms. And so if we convert this to metric tons, each metric ton has 1,000 kilograms. We're at 97,200,000 metric tons of copper ore. So now we got to figure out what the mass of this pure copper is, because we know that it is 1.2%. If we multiply our whole shebang by 0.012, we're up to 1,166,400 metric tons of pure copper. So that's what we're going to make money on. So let's figure out how much money that is. So we take that number, multiply it by 9,000, and you get quite a lot of money. Excellent. $10 billion, basically. So then we gotta figure out the cost. Go back. We already know how much the mass of the mining area. We figured that out already. So we take that number, multiply it by $60. We get $5,832,000,000. We add in the environmental remediation. That was a one-time cost of $2 million. And so that's where we're at now for how much this is going to cost us. $5,832,000,000.
834 million. So now we take the amount of money we made minus the amount of money it cost, and this mine's going to make that CEO 4,666,600,000. That's pretty good. So if we want to figure out our cost benefit ratio, that would just be the total cost divided by the total revenue, which gives us a 0.56. And so anything under 1 is going to be profitable. So this would indeed be a profitable mine. Nice work, everybody. You made it to the end of this video. I have here the part 1 video that goes with this in case you missed that, as well as another video here that could be used as a extra material on renewable resources. So that's all I got for you guys. I hope you had a good time and take care.